So yeah, morning is really long name, I know. So my name is Hsun Yang. I'm like talking about the topic of like LiDAR perception, especially in pedestrian. So I'm going to introduce myself a little bit. I joined National Physical Laboratory in 2022. And I'm now part of nNPL's Assured Autonomy team. One of our previous work is actually the weather, like sensors degradation on weathers. So we work with the Met Office, and the result was presented last year in AutoSens as well. And before nNPL, I was a solution engineer in like semiconductor and automotive industrial. I'm mostly working on the VMV measurement application. So this is today's agenda. And in this experiment, we are aiming to see the performance of 3 different software products. The first one is Solar Robotics Sensor 3.2.1, and the Hsun Shift Perception 4.30.0, and Cornea SenseH 1.5.0. The reason why we provide the quite detailed software information here is the performance in each version might be different. So, yeah, the algorithm inside this perception software perception box is black box to nNPL. So the way we verify the software's capability is based on a pass-fail test of certain ODD, certain scenarios. And this product, they are meant to be deployed as part of the infrastructures. So the ODDs in this work are limited to a common zebra crossing user scenario, for example, like parallel walking, walking ramp, wheelchair. And so you might see this graph before, I mean, the right-hand side one. So under this SAE's definition, to reach a higher level of autonomy, a vehicle must be communicate with the infrastructures. It's due to a very fundamental limitations. Let's say if your car is about to right turn, it's very unlikely you can know what's after happen after the corners. So the concept of autonomy through infrastructure comes in. And I believe this term was first introduced by one of the manufacturers, Solar Robotics, 2 years ago. And this approach, I mean the autonomy through infrastructure approach, is not only cover up the blind side of the vehicle, but it can also offload the heavy computation and sensor requirements from each individual vehicle as well. So of course, we want to know why these boxes they work with LiDAR. Firstly, because deploying LiDAR have less privacy concern if you deploy LiDAR as part of infrastructures. And also LiDAR's resolution can provide very good outlined shape of an object, but it does not capture 2D detail, for example, your facial features or your car plate numbers. Secondly, unlike a single normal 2D LiDAR, 2D radars or cameras can provide 2-dimension information X, Y, or XZ. 3D LiDARs can provide precise X, Y, and Z information. Of course, you can find some more fancy frequency modulated LiDARs. They provide also the velocity, distance as well. Other reason including the LiDAR provide a better range compared to cameras, and LiDARs also have better output under like harsh lighting conditions. Next, I'm going to go through the measurement setup, including the environment setup, the LiDAR specification, and the ODDs. So we simulate a like everyday road crossing scenario. You can see in the UK on our like nNPL's outdoor lab. We have placed zebra crossing mat on a 7-meter wide road. The LiDAR is mounted 5 and 10 meters away from the zebra crossing mat. The LiDAR, the LiDAR is placed on a height of like 2.1 meter, and then it's tilted angle to 30 degrees in 5 meters and 7 degrees in 10 meters, which point to half of the height. So we are focused like the center of the mannequin, and the mannequin is like 1.8 meters. Yeah, 1.8. In this experiment, the LiDAR we're using is Ouster OS1, 128 channels version, and recording in a 10 hertz frame rate. The range of OS1 is 90 meters. The vertical and horizontal field of view are 42.4 degrees and 360 degrees. Both the vertical and horizontal angular sampling resolutions are 0.01 degree, and the range resolution is 0.1 centimeters. So we define the ODDs based on BSI's taxonomy, with 3 top-level attributes: the scenery, the environment, and the dynamic elements. The scenery is set to a regular 2-lane road with a zebra crossing, and the ODDs cover mild rain and mild wind with a summertime daylight. Some traffic is going on in the background, and 1 or 2 persons walk across the road. We designed 22 user cases, and 8 out of them are static. The rest of them are dynamic. The static ones including the mannequin standing with a walking frame, the mannequin sitting in a wheelchair, and then the mannequin lying down on the floor, just basically on the zebra crossing. So 4 out of 22, like 4 out of like the rest 14 dynamic test case are the a real like actual person only. So one of like our colleague David, he's also about the same height as the mannequin, so it's 1.8 meters in height, and he walked across the road with the walking frame and then with the wheelchair. The last 10 test cases are combined like both mannequin and a real person. The first is the mannequin sitting in the wheelchair, and the second person push it. The next one is the pedestrian waiting to cross the road next to the mannequin. The waiting time is 0, 5, 10, and 20 seconds. So, yep. The most important part, the result. So the definition of pass-fail in this test is whether the software can see the targets. The targets is the real person or the mannequin. And be aware of the result. They are only been through a basic calibration. So no matter what's the minimum calibration required by that specific product, we only went through that. And this is because we want to see like the experiment is meant to find the overall ability as benchmarking of this product, this kind of products. So therefore, it's possible to have like more accurate, better results if you do like fine tuning or like a more comprehensive calibrations. So the first one we are looking is the soul robotics sensor, and it went through the ground alignment as the calibration. It passed 12 out of 22 test case. A few points worth mentioning are the working person in some cases is split to like several parts, and 3 test cases have like more than 100 false positive targets, and in almost all the past cases, the mannequins or the person is classified as other than a pedestrian. The object also identified as more than like one targets, like it's identifies like multiple objects. Yeah, I will share more on the following slide. So this table shows that the sensor is doing well in dynamic and mixed cases, and none of the stated cases is identified. The result is potentially caused by the algorithm. It's mapping the environment in the beginning of the measurement. So the static object, they tend to merge into the background. The result from both like 5 and 10 meters are pretty consistent. The working person are identified as miscellaneous, cars, cyclists, and pedestrian. While walking, the classification like of the object changes as well. The object IDs also changes. This means the person or the mannequin is actually not the same objects to the system. The highlighted test case here are the case have more than 100 false positive targets. We don't know the reason yet, but possibly related to the shape of the target. So it's happening on the working frame and then the wheelchair cases. So it's potentially like related to that. So in this slide, some videos can show you the points I have mentioned in the previous page. So this is on the left, the video, you can see the raw data. And then on the right, it's what implemented the algorithm. So you can see the right-hand side one. The upper body, the working person's upper body is split, like from their lower body. And then the clutch tag, which is the green one, the clutch tag, is attached to the upper body instead of like the lower body. So this might indicate that the algorithm use the upper body to identify a pedestrian. So this video, you can see the classification changes. So the red one previously you see is a car, and then right now like the The white white color one, it's miscellaneous. And then the green one, it's pedestrian. So the class ID associates with this entire process. So from car to miscellaneous to pedestrian also changes. So for the system, this walking pedestrian throughout the process is actually identified as 3 objects. And on the right is a typical false positive target situation front sensor. You can see in the background there are like a few trees there. These trees, because of the wind, they're moving, so it causes some like false positive. Some go away like really quickly within a second. This can probably quite easy to remove, but some quite persist, and this will be the kind of like the false positive target that will cause issue to the autonomous vehicle. And then we move to the next product, the outside shift perception. Let's run through 2 calibration process. The first one is generated a reference map for 5 meters and 10 meters setup. The way we generate it is from a pre-recording data through the environment. The second one is to define the ground plane. The reference map generates based on the predefined operating context, which is medium all-terrain context. We try other contexts like large all-terrain or all-flat other contexts as well. The result is pretty much the same. And it passed 9 out of 22 test cases. The product takes a longer time to identify the objects, or we can say a narrower identification windows. We cannot tell which is the case in this experiment, but I will show you more detail on the following slide. And the shift perception has the issue of like misclassifying and the multiple objects issue as well. So the shift perception is more sensible to dynamic and mixed test case. Distance is a factor in this product. It did slightly better in 5 meter test case than the 10 meter test case. This product does less misclassification, although all the test case have been identified as miscellaneous, but the class is limited to person and miscellaneous, so like no cars or like other than that. The two-wheeler only happens in the wheelchair cases, which makes sense because there is a person and then two-wheel. The number after the slash is the time it takes to identify the object. So if we minus the time to the waiting time, the range is from like 4 to 10 seconds. And considering the road is like 7 meters wide, the deviation is, we can say, relatively large. And since the targets, they are most identified by end of the road, like end of the zebra crossing. So this could associate with the recognition window, like maybe under certain angle, it's easier for the product to recognize. So it's a 5 meter walking scenario. You can see the algorithm identify the pedestrian when he approached the end of the zebra crossing. And this happened in the 10 meter walking scenario as well. So this is the 10 meter one. And then it's the same situation. Plus, you can see the object ID changes from like 12 to 13. So even it's just recognize the class doesn't change. It didn't change, but it's still being like 2 persons to the system. So this is a 5-meter walking person push the wheelchair cases. So both the wheelchairs and the person are like recognized by the end of the zebra crossing. The barrier here, was recognized as a 2-wheeler and disappeared shortly after the wheelchair parked there. I think this can explain the challenge of this kind of real-time recognition, how hard it is. You need to remove the background, classifying, and then doing the rest of the sending out, the calculations. So the last one is the sense age. The sense age is went through the fine auto-aligned calibration. It passed 18 out of 22 test cases. A few things need to point out about this product as the object IDs change a little more in some test case. In the walking next to, like the waiting next to mannequin test case, the mannequin's identification is correlative to the pedestrian's movement. The wheelchair is identified as a bicycle in 5 meter. However, it became an adult in 10-meter test case. So the sense age passed all the dynamic and mixed cases and half of the static case. In the static case, the distance is a factor of performance. Even the test case have like a little unconventional movement, like walking ramp, it has passed. So overall, sense age can cover most of the scenarios we designed. However, in the mixed cases, the object ID changes happen in almost all the test case. You can see the highlighted here. 9 out of 10 had this issue happening. So the video show like how the movement of the pedestrian impact the identification of the mannequin. So the mannequin technically standing here. So the mannequin is visible to the system. However, to recognize it, it requires the movement of the walking person. When he passed, the mannequin appear, but when he gone, the mannequin disappear again. So this is the, you can see the object ID of the wheelchair change before and after the pedestrian pushing it. So this is a 5-meter wheelchair mixed test case, and the wheelchair is classified as a bicycle here. The next video is the same scenario, but in 10-meter distance. And it became an adult instead of like a bicycle. So also the object IDs changes when he like start pushing the wheelchair. So today we provide like an overview of the performance of LiDAR perception software product. You can learn that static object still be like quite challenging to these products. The misclassification and then false positive objects happen quite often, I would say. So to closing, I think you may heard of the accident of the autonomous vehicle that was operating in San Francisco. So we are not going to go into detail here. Long story short, a pedestrian was hit, was struck by a hit and run cart, and then it was thrown into like another adjacent light, and then was hit a second time by an autonomous vehicle. So the pedestrian was classified as an unknown objects. So you can see like suppose that the software can identify the pedestrian earlier, or like the classification it's correct, the maneuver it takes could be completely different. So I hope like through today's presentation, you can learn that why we like nPL feel it's important, and raise some of your interest and concern about how we can assure the entire like autonomy systems. Thank you for your listening.
Thank you very much. Hsun, thank you very much for these deep insights. I mean, I was quite already from the previous presentations, I already got some concerns about the weather conditions on LiDAR. This is even more concerning, to be honest, to see every single LiDAR, what's going to give us a different kind of perception and misinterpretation of data. In the interest of time, I would like to motivate you to catch up with Hsun during the coffee break to ask questions if there are any questions available, and for the rest, I'm looking forward to welcome you back at 11 o'clock after the coffee break. We're going to have some, let's say, more insights from Joel about what the future of LiDAR is towards in the automotive industry, which basically concludes or is the next step of your test results. Hsun, thank you very much. Thank you.